Your mic's on, right?
Hello.
Go
Okay, our second speaker is Roy Bell, and Roy is a second-year master's student under Professor Palawa, and he works on power electronics with applications to renewable energy. And unfortunately, we'll be losing him this August, and he'll be going to the University of Minnesota, where
Treachery.
yeah. So we wish him all the best there.
Thanks. Right, so today I'm going to talk about a maximum power point tracking algorithm I've been developing for PV application. It uses differential power processing, and it's asynchronous and distributed. And I'll talk about what I mean by asynchronous, and I'll also briefly go over what differential power processing has to do. Okay, so just a brief outline what I'm going to talk about. So I'm going to go over some of the main PV power management topologies that have been used throughout the years. Talk about differential power processing coupling, which ties into the asynchronous part of my title from the previous slide, and then go over my proposed maximum power point tracking algorithm, which sort of handles this coupling issue, and then present some experimental results. So here we have three different sets of power management topologies, and a table below sort of giving a comparison between the three different sets. So to the left, we have your conventional power management topology that uses bypass diodes. And I'm not going to go over each thing in detail. I'm just going to talk about them as quickly as I can. So with a conventional topology, you have bypass diodes that sort of ensure that its corresponding panel its voltage doesn't go negative, such that it's not sinking power. So when your string current increases well above the maximum power point string current of a particular panel, that corresponding bypass diode shorts out that panel, and you lose that panel. So you lose out on energy generation. So your system efficiency is pretty poor. And additionally, you can't actively track the maximum power point of each panel. So in order to, a solution to that problem is using DC optimizer microinverter topology, which are the two different architectures in the center column. So these topologies sort of detach the series panel connection and place a power converter directly in parallel with each panel, and that power converter actively tracks the maximum power point of its corresponding panel. So your system efficiency is greatly improved, but it's at the cost of using hardware that needs to process that entire power, which can be on the order of like 300 watts. So your hardware requirement is like substantially increased. And also, because you're processing the power from that panel, you're potentially losing out on a lot of energy. So say each converter is 95% efficient, and the power generation from the entire module is 300 watts, or say like from all three modules is like a kilowatt. You would lose 50 watts if each power converter is 95% efficient. So a solution to that is the differential power processing topology, which basically relies on the fact that the mismatch between each panel is usually small, so you only need to process the mismatch in power to actively track the maximum power point of each panel. So say like in the PV to PV topology up here, the top panel is maximum power point current is 5 amps. The one below that is 4 amps. The DPP, the top right DPP would only need to inject like 2 amps, and then this would need to be like 1 amp. So the amount of power they get to process is like greatly reduced compared to like a DC optimizer microinverter topology. So consequentially, your system efficiency goes up because you're losing out, or because your loss is reduced, right? But the problem with this topology is that it's somewhat hard to control because of a problem that I'll talk about in detail in a few slides. It has to do with coupling. So because of the way these DPPs are interconnected, that can induce coupling, and whenever you want to do maximum power point tracking, it can affect whenever one converter perturbs its state, it can affect the states of all converters in the string. And this is what this slide sort of illustrates. So say you have the PV to virtual bus topology, which is a differential power processing topology, and the PV to PV topology. So say you have 3 submodules. The third submodule has greater power generation than the second has greater power generation than the first, and then as a result, you have these converters are processing power as follows. So whenever you want to do maximum power point tracking, oh, also I should mention this. So like in this topology, you can see that by power conservation, when this power injected onto this bus plus this power injected onto this bus is equal to the power that's absorbed from this converter. So whenever you want to do maximum power point tracking, say like this converter perturbed its state, sort of illustrated by this power versus submodule voltage curve. So this converter perturbs its state, so it changes the amount of power that it's processing, and as a result, because of the coupling, it changes the amount of power that these guys are processing. So this perturbation of this one converter not only changes the state of its corresponding panel state, it changes the states of all panels in the string. And likewise for this topology too. It's a little bit more complicated, but I'll leave it at that. So yeah, like I said, the perturbation of one converter affects all submodules, and the submodule state is a function of all states in the string. So maximum power point tracking usually requires like some form of like global information about the impact of all perturbations on whatever this converter is measuring. And that usually requires like neighbor-to-neighbor communication or potentially global communication. And that has been explored with this topology for the PV2PV group here at Illinois. And they've developed a maximum power point tracking algorithm that deals with that coupling using communication and like deconstruction of like all that information. So what I'm going to propose though is like an actual physical attenuation, which is facilitated by this topology. And I'll show what I mean by that in the next few slides. So here are some simulation results. This was done in Plex using the Plex block set in Simulink. This is the PV to virtual bus architecture. I made the input and output capacitors of each converter explicit. So you have CPV is the input capacitance of any one of these converters, and it's 10 microfarads. And then CBus is the aggregate output capacitance of all of these converters, and that's about 30 microfarads. And I set the characteristics of all these three panels to be such that 3 and 2 are equal. The maximum power point power of 3 and 2 are 37 watts, and the maximum power point power of submodule 1 is 25 watts. So what happens here is, say you're in steady state before 2 seconds, you have that PV2 and 3 are generating this amount of power. It's about 34.9 watts. PV1 is generating about 24 watts. And consequentially, you have that PV or DPP3 and 2 are processing about 3.6 watts, injecting that into the bus. And then you have that DPP1 is absorbing that power in that direction. So at time 2 seconds, you have the DPP1 perturbs its state, and that results in a change in the amount of power that it processes. And you can see that affects the amount of power that's processed by these two converters. And as a result, that changes the state of those two converters in addition to the state of that corresponding panel. But for a brief moment of time, you have that the bus capacitance is sourcing or is sinking that amount of power. And that's just because these converters are inductive by nature. And if you think about it, for those of you taking 598, whenever you have a load step for a power converter, the capacitor sort of sources that load for a brief amount of time, right? Because the inductor needs to catch up to that load transient. The same thing here. So you have that this converter is sort of introducing a load transient to the system, and the bus capacitance for a brief amount of time, it sources or sinks that amount of power, and such that it's. But in the long run, these guys catch up to that, and then everything sort of just couples together. So what does that look like when you zoom in to 2 seconds? You have that bus capacitor is sinking power for about 1 millisecond, and it decays according to a time constant calculated by this equation. So you have P bus is equal to V bus times I bus, and then you use the capacitor current equation, plug it into there, and you sort of rearrange terms, and you get this expression for how fast this guy decays. and that's a function of, that's directly proportional to how big your bus capacitor is. So for small bus capacitance, this will sink power like for a really brief amount of time, and then everything will settle really quickly. So what I'm proposing is sort of just increasing this to be sufficiently large such that on small time scales, the bus capacitor is like compensating that perturbation, right? And it's attenuating the coupling between all of these submodules and converters. So here's some results for a bus capacitance that's 1,000 times larger. It's like 30 millifarads. So what you have is the same sort of situation. At 2 seconds, converter 1 perturbs, and over about like 0.2 seconds sort of corresponds to its time constant, and yeah, it's no longer an impulse. It holds on to its sourcing power, or its sinking power, for a much longer amount of time. And if you sort of zoom in for around 2 seconds, like plus or minus 1 millisecond, you'll see that as soon as converter 1 perturbs, it changes the amount of power that it's processing by about 60 milliwatts. And that power is exactly equal to the amount of power that's injected onto the bus. And that doesn't affect the 2 converters above it. And consequentially, that doesn't affect the states of those 2 converters. It only affects the state of the corresponding submodule. So you can take advantage of this characteristic to sort of do maximum power point tracking locally and irrespective of each other. So like, and I'll show that in the next few slides. So this next slide shows 2 perturbations. So like, it's the same situation at 2 seconds. Converter 1 perturbs, and the bus capacitor compensates all of that power, and it doesn't affect anything else in the string. And then a millisecond later, you have the converter 2 perturbs, and that changes the amount of power that it processes, and thus changes the amount of power that its corresponding submodule generates. So you can do this, you can perform a maximum power point tracking algorithm locally and irrespective of each other, and such that like if converter 1 perturbs its state, it doesn't affect the other submodules, and it knows that if it perturbed in one direction, it decreased the amount of power that its corresponding submodule was producing. So it knows that it needs to step in the opposite direction on its next perturbation iteration. Great. So, but what happens in the long term is shown in the next slide. So you see that you might run into the situation where you're just continually building up power onto the bus, and that's what's shown here. So what's shown here is it's the same maximum power point tracking or maximum power point distribution as the previous slides. You have CPV is equal to 10 microfarads, C bus is equal to 30 millifarads, and right after 2 seconds is when maximum power point tracking starts. Stuff before it is just some like initialization stuff for the simulation. So at 2 seconds, maximum power point tracking starts, and you can see that submodules 2 and 3 are tracking 37 watts, and submodule 1 is tracking 25 watts. But that comes at the cost of just continually injecting more and more power on, or I guess constant amount of power onto this bus, which continually builds up the amount of voltage that the bus has over time. So what you can do is you can change, you can regulate the amount of power that is injected or absorbed from this bus through the central converter, and I'll go through some math that sort of illustrates that. So here is the same PV to virtual bus architecture, but it's generalized for N submodules, and the grid connected inverter and the grid are just left out, and I'm just showing the string voltage and the string current. String voltage is just the input voltage into the central inverter, and the string current is the current that's going into the central inverter. And then I'm showing all the states as well, just for the sake of showing where all these terms come from. So P string is equal to V string times I string. You can see that V string is equal to the sum of all these submodule voltages, and I string is equal by KVL, and I string by KCL is equal to the difference between a submodule current and its corresponding current processed by its differential power processor. And if you distribute that, you get this line, and then you can just call VI II is equal to PI, which is the submodule power generated. And additionally, you can say that VI times I delta I is just the power that is processed by any of these DPPs. And if you assume that all of these converters are ideal, then the input power is equal to the output power, and you can say that the sum of all these powers is equal to the power injected into the bus, which is given by this relation right here. So if you rearrange terms, you get this expression. The power injected into the bus is equal to the sum of all submodule powers minus the string current times the sum of all submodule voltages. So at maximum power point operation, in steady state, you should have that the power injected into the bus is 0, such that the voltage on the bus is constant or it's oscillating around some average value. Right, and if you set that equal to 0 and you assume maximum power point operation, then you have that each of these submodules that is at its maximum power point, which is denoted by this NPP subscript. And I'm just showing that there exists a string current that achieves 0 bus power injection, and I'm calling that I string star, and that's just equal to the sum of all maximum power point powers over the sum of all maximum power point voltages. So this little conditional block sort of shows how P bus is affected by the current, the present string current in relation to this maximum power point string current, or I string star. So whenever I string is equal to that particular current, you have 0 power injection onto the bus. Whenever I string is less than that particular current, you have positive power injection, and conversely, you have negative power injection, or you can say the net power is absorbing power from the bus whenever I string is greater than this particular string current. So how does that affect the bus voltage? It affects it through this equation. The bus voltage is positive, the capacitance is positive. So if the central inverter can measure this voltage, it knows that whenever the bus voltage, say, is increasing, then that corresponds to a positive power injection onto the bus. And then it can look at this table and determine that I string is less than this particular current, so it needs to increase the amount of string current to get to this point and eventually get to 0 power injection onto the bus, which would achieve stability. So having that said, that's how you would basically achieve stability in the system. You just control the string current by monitoring the bus voltage to ensure 0 power injection onto the bus. So how do you do this distributively? So on the previous slides, I was just showing like the maximum power point tracking algorithm, sort of under the assumption that each DPP had access to its particular submodule's power generation. So how do you actually calculate or measure that power? So that's what I'm going to talk about in this slide. So each DPP can like losslessly sense its corresponding submodule voltage, and if you have access to the submodule current, then you can calculate its corresponding submodule power. So I'm just going to show that you can directly calculate this submodule current if you have access to the string current. So the central inverter is already measuring the string current, and the central inverter is at the same potential as this ground. So because this potential is isolated, it can just arbitrarily be chosen to be at any level. So if you tied together this potential and this potential, you have the bus potential is at the same potential as the central inverter. So you can directly communicate the already measured string current from the central inverter through the bus to all of these differential power processors without using isolated communication or like any sort of like fancy way of communicating that value to these guys. I mean, you can also do like power line communication too. Like this bus sort of just facilitates communication between all differential power processors. It's a nice feature of this topology. So each DPP now has its submodule voltage and string current, assuming that line of communication exists. So now all it needs is this current right here to be able to directly calculate the submodule current, and that's desired. I mean, that's not a huge trade-off because the amount of current this is usually pretty small, because in DPP this just leverages the fact that in DPP that current is usually small. So the amount of loss that would incur from using like a resistive current sense amplification would be small as well. So what you can do is each DPP can sense its process current, its submodule voltage, and if it has its string current communicated through the bus, then it can calculate the submodule current, and then it can directly calculate its corresponding submodule power, and then it's pretty like trivial from there. It's just a matter of doing a direct maximum power point tracking on that particular submodule. So just a reiteration of the control objectives. So each DPP is locally maximizing its submodule power, and the central converter is regulating the bus voltage by varying the string current, as shown by the math in the previous slides. So here's some hardware. To the left, top left is a PCB with 3 flyback converters, where each flyback converter is just the differential power processor shown here. So this is really just 3 converters stacked on top of each other, and they're all on one PCB. And to the right is just a schematic representation of how that looks. This is the efficiency versus load currents. So above about 0.6 amps, you have, that corresponds to about 7 watts because this is at 12 volts. So above 7 watts, you are above 90% efficiency. And the efficiency peaks out at about 2 amps, which is about 94.5%. So below 7 watts, you're in the light load region, and like the efficiency is like pretty crappy. And that's something that I'm working on right now to improve. This is an off-board microcontroller from TI. Has like low-pass filters before the EDC for just improving signal integrity and all that stuff. And this is just a component listing table of everything that's on this board. So here's an experimental setup. You have 3 submodules where each submodule has a power supply, a current limited power supply connected in parallel to it, and this basically allows you to emulate PV characteristics for any desired insulation level. And here's a bunch of digital multimeters. They're connected through GPIB, and it was really slow, so like the measurements aren't as good as they could be. And those are relaying that information to a PC. Here's the PCB I showed on the previous slide, just with the 3 flyback converters connected in this topology. Here's a really, like, I'm using like a 50 millifarad bus capacitor because I'm using GPIB, everything is really slow, so you need a really big bus capacitance. So like in the future, when I can start like speeding things up a little bit more, I can reduce this guy quite a bit. And here's the launchpad I showed on the previous slide. And basically, what's controlling the string current is just an electronic load, which is communicating with the PC through digital multimeter measurements through GPIB. And here's a list of all the equipment and system parameters for this experimental setup. So here's an experimental MPPT for 30% mismatch. So we have that the third submodule's maximum power point is 37 watts. Second submodule is maximum power point is 36.5 watts, and so on. There's a bunch of other stuff. So like the way this works is it's broken down into 4 different regions. These first 2 regions sort of just initialize everything, and this guy basically ensures that the amount of power that's initially injected onto the bus or absorbed from the bus is minimized whenever you start actually doing maximum power point tracking. Because as you can see here, the string current is too low. So whenever you start doing maximum power point tracking, the bus voltage like really starts to climb up, and the string current needs to increase to sort of counteract that by the equations I showed on the previous slides. So once the string current sort of reaches this value here, the bus voltage sort of comes back down to this reference bus voltage, which is about 10 volts, and I wanted it to be 10 volts because I wanted it to be equal to about the maximum power point voltages of the submodules used. And then they both just start oscillating with respect to each other to sort of regulate the bus voltage. So the maximum power point tracking efficiency of this topology is 98.39%, and that includes like the insertion, like the converter loss as well. So that's just a product of the conversion losses and the tracking efficiency. So I still need to measure the actual tracking efficiency, but yeah, it's still much better than like the conventional like no DPP solution that just uses bypass diodes. It's like 12% better. Future work just includes improving the light load efficiency. If you sort of just look back at this curve, this is pretty awful, and these converters are usually processing like a really small amount of power anyways, so you should have a really good light load mode control to improve this guy, really. Reduce the amount of required bus capacitance, so I'm using a bus capacitor that's like this freaking big, and it's like 50 millifarads. So hopefully I can like, and that's like an off-board thing too that I need to connect to my PCB. So hopefully I can reduce that by like an order of 50, and it kind of, I'm doing that right now at the moment too, and it's looking positive, and I think I can just make it like an onboard capacitor, just a bunch of ceramics. And finally, just get some field data. So everything that's been shown so far is just like in lab or simulation, but I think that, I mean, this sort of just doesn't mean anything until you get this out into the field and you actually show that you can do maximum power point tracking for a string outside of the lab. Questions? Yep.
Is this more suited for microinverter applications?
So the amount of capacitance that you need is just determined by, I mean, if you have, say, like, if you have three DPPs, whatever capacitance you need for that, it's not like you would need to increase it, because like that is just going to be connected to the output of that particular PCB, and then that would just sum up with all of the other bus capacitors. So like you'll have like a total bus capacitance on each PCB, and then that'll just put them all in parallel, and you'll increase the amount of bus capacitance you have that way. And also, I mean, like, yeah, I mean, it's not necessarily just perfectly suited for like the microinverter connection. I mean, I think it could work with like really long connections as well. But the downside to this is that you need two differential wires as opposed to one for the PV to PV architecture. Huh?
Your last experiment, you put together to have 37 and 25 watts of that big mismatch.
In the fields, it's probably not very real. I mean, it's usually like on the order of like 20 to 10 or something. I'm just showing this because it basically just increases this difference and makes this algorithm look better. You know, I'm not gonna like sugarcoat anything. I mean, really, like, I'm not gonna say anything else with respect to that, but you know the deal. Yeah. 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 What's up?
You have shaded panels with that.
Yeah. I mean, but if you're like out in the field though, like, I guess it depends like how the system is oriented. If it's just out in the field, then you kind of don't have that much shading, right? But if it's like residential, then I guess you can run into problems like this. So I guess it really all just depends on how or where this system is being placed, right? Yeah, what's up?
Maybe you mentioned that this is future work, but how close, when you adjust the string current,
Uh-huh.
how close does that stay to like the optimal string current? Or does that even matter?
Yeah, so I mean that would induce ripple in the output, right? Yeah, exactly. So I mean one thing you can do, so like I think right now, I did this experiment quite a while ago. I think my perturbations for the string current was like quite big. It was like maybe on the order of like tens of milliamps or something. I mean, I think realistic, like in practice, it's much smaller than that. It's like usually on the order of like a milliamp or something. So then like your oscillations would come down quite a bit. Yeah.
So this would not work with like, you couldn't put this in a system that's already just right communication from the system.
Yeah. So I mean, that's like another downfall. So like I think really two drawbacks for this topology is that you need two differential wires, and you need communication between the bus voltage and the central inverter.
If you maybe just like retrofit like an extra device to do the measurement, like you need to protect the control of the central inverter, you just need information.
Wait, what was that?
So you just need information, or you need to actually adjust the way that the centralized inverter does its control. Like if you just add like an external measurement device that sort of replicates the measurement communication of the centralized inverter.
Yeah, I think you can do. I mean, really, all you need is the central inverter just needs the bus voltage, and the DPP just needs the string current. So I mean, it's just two lines or two things. That,
Aside from that string current, will this work with the pre-existing inverter?
wait, what do you mean exactly?
So suppose you got the information for the string current some other way.
Uh-huh.
Would this work with pre-existing inverters, like the way that they handle maximum power point tracking? Drop it.
with just a microinverter?
Like a standard centralized inverter.
Oh, no. I mean, you have to the central inverter needs to know that this DPP
Just control even as well.
Yeah, because I mean, just like in a traditional maximum power point tracking topology, like the central inverter is basically just slowly changing its string current such that it's like tracking the maximum power point. But here it's doing it differently. It's changing the string current to regulate the bus voltage and ensure stability. And it just so happens that that particular string current is the maximum power point string current, just by the math that I showed. Any other questions? No? All right, thanks.
Yeah.